Yay!
All right, for the ideal gas law, let's start out just by showing how to put numbers into the ideal gas law, because this is the single greatest source of error for most students when you put the numbers in, like what units to use. So let's go over just a real simple example. Let's suppose we have a 2-liter bottle, just like of soda, and it's empty. I mean, not it's empty of liquid. It's got air in it, right? That's the point. So suppose it's just a 2-liter bottle of air. Let's see, 2-liter of air. Let's see. The ideal gas law is going to let us calculate how many molecules of gas are in the bottle, which is kind of a cool thing. How many molecules of air in the bottle? Okay, let's see. So what we're going to do first is write down the ideal gas law. All right, so ideal gas law is pressure times volume. I'm going to write it down in, sometimes it's called the physicist's way, and then I'll show you how we get to the chemist's way, which is actually more useful. So the physicist might write down NKT. And so just to be clear, N is the number of, be careful, it's the number of molecules. It's the number of particles in the gas. That's sort of what we're after at the end. That's kind of what we're going to be solving for. K is our Boltzmann's constant. Some people put like a B underneath it, but I mean, context is going to make this kind of clear. The trouble is that in physics we use lots of different Ks, right? There's like spring constant. There's the K. You'll see another K when you do electricity and magnetism. So unfortunately, the same letter is used for lots of different numbers. This is called the Boltzmann constant, and it's 1.38 times 10 to the minus 23. The units are going to have to be joules per Kelvin. Which means that T better be in kelvins, right? So far we've been getting away with a lot of things in Celsius, but now we're going to have to use kelvins. The reason why this might be obvious, maybe it's not. What the 0 point of 0 Celsius is freezing water, but that's a little bit arbitrary, right? What does water have to do with it? It's just convenient because most of the temperatures on Earth that we're normally encountering are not that far away from freezing water, between freezing water and boiling water. So that's just, it's sort of convenient. So that equals 0. The trouble is that we're going to identify temperature as the average kinetic energy of the molecules. So if temperature is the average kinetic energy of the molecules, remember kinetic energy was 1/2 mv squared, right? Just as scratch work, 1/2 mv squared. Well, nothing about that is negative. Mass can't be negative. We're squaring the v, right? So temperature can't be negative is what I'm saying. So to have something at minus 10 degrees in physics really doesn't make much sense, because that would mean, there's no negative mass and the negative velocity. There's no negative kinetic energy, right? The lowest it can be is 0. So as a material cools down, its molecules are going to move slower and slower until their motion essentially stops. And that should be 0. That should be 0 temperature. So that's what we're going to call absolute 0. It turns out that you can measure what this should be, and we'll talk about that maybe in a subsequent video. But experimentally, it's been determined that absolute 0 is about minus 273 is 0 on the Kelvin scale. So really, 1 degree Celsius is the same as 1 Kelvin, right? The units are the same. They just start in different places. So to get from one to the other, you just add 273. So if I say it's 30 degrees Celsius outside, then that means it's going to be 303 kelvins. I just add 273. So Kelvin is Celsius plus 273. That's all there is to it. Oh, by the way, I'm trying to be careful. Sometimes I slip up. No one says degrees Kelvin. That makes you sort of like a physics toddler. So if you want to sound sophisticated, you say kelvins is the unit, because it's like an energy. So you can say degrees Celsius, that's fine, but nobody really says degrees Kelvin. You should just say kelvins. But anyway, small point. All right, so when you put temperature into physics equations, it should be in kelvins, no negatives. If you're putting in a negative, something's very wrong. All right, pressure is in Pascals, which is an SI unit. It's 1 Newton per meter squared. A common unit of measurement of pressure is an atmosphere. So sometimes you'll see things, because most of our experiments are done, in an ordinary laboratory where there's 1 atmosphere of pressure everywhere. So that's sort of a natural thing. But the conversion is that 10 to the 5th pascals is 1 atmosphere. So if you're going to plug 1 atmosphere into the ideal gas law, you better use 10 to the 5th. Not 1. You're going to be way off, right? That's 100,000, factor of 100,000. And finally, and then we'll get to a real calculation. V. What the heck is V? V has to be in, it's an SI unit, right? So it's got to be in cubic meters. Okay. And just with a little bit of scratch work, let's see how that works out. Because a lot of times you're given like volume measurements in liters or something like that, which is a metric unit, but it's not cubic meters. Okay, so let's go over this real quick just to make sure we're all on the same page. If I have a little box, and this is 1 centimeter, 1 centimeter cubed. This is 1 cubic centimeter, right? So how many cubic meters is this? Well, each side, let's see, it's a centimeter, right? So it's 10 to the minus 2 meters, but I got to cube it. So this is going to be, what is that? It's 10 to the minus 6th cubic meters. There are 1,000,000 cubic centimeters in a cubic meter, not 100. Be careful of that. So you have to cube the thing. And by the way, this is also called 1 milliliter. That's the connection. Okay, so now take something bigger, not to scale. So here's another box, and let's see, this one is 10 centimeters on a side. All right, so if it's 10 centimeters on a side, now I've got 10 centimeters cubed, right? So that's 1,000. So that's going to be, each one of those is a milliliter. So this is 1 liter. Okay, so a liter of volume is something that's 10, it's a cube, 10 centimeters on a side. And this is going to be 10 to the minus 3 cubic meters, right? So finally, when you get to the end, if something is 1 meter on a side, a cubic meter, that's 1,000 liters. So that means that something that's 1 cubic meter is 1,000 liters. Okay, so we're going to have to remember that conversion. So 1 liter, oh, I've already written it. 1 liter is 10 to the minus 3 cubic meters. Okay. The reason I want to go through all that is because we have a 2 liter bottle of air. Okay, so let me just kind of divide that out. All right, so finally, we can do the calculation. All right. I want to know N, right? The number of molecules. Okay, so here we go. So the number of molecules is just going to be PV over KT. And so that's going to be 1 atmosphere, right? Just an ordinary bottle sitting on the counter. So this is going to be 10 to the 5th. And the volume is 2 liters. All right, each liter is 1,000th of a cubic meter. So this is going to be 2 times 10 to the minus 3 cubic meters up top. All right, K is going to be 1.38 times 10 to the minus 23. I'll suppress those units. And T, okay, I don't know, a normal sort of a room temperature that I like to use is 300 kelvins, because that's like, what is that, 27 Celsius? I don't know. That's maybe a slightly warm room. Sometimes people define room temperature to be 298 Kelvin. Well, that's kind of a tough number to work with, right? 298, just call it 300. It's easier to work with. So 300, there's our room temperature. Okay, and if you multiply all these numbers together, what did I get? Something like 4.8 times 10 to the 22 molecules. Cool. Okay, so that'll tell you how many molecules there are. Now, another number, another quantity that we're going to be working with a lot is called moles. How many moles is that? 1 mole is about 6 times 10 to the 23rd molecules. I mean, it's 6 times 23rd anything. So if I have 6 times 10 to the 23rd pencils, I've got a mole of pencils, right? It's a unit of a collection of things, sort of like a dozen, or a couple, or, you know, whatever, or a gross. What the heck is it? 144? Is that a gross? Okay, so a mole is 6, really it's like 6.02 times 10 to the 23rd, but I don't care. Let's just call it 6. It's close. Okay, so how many moles do we have? If I just divide those two things, 4.8 times 10 to the 22 divided by 10 to the 23rd, this means I have something like 0.08 moles of air in the room. Really, the number of moles is what's usually used in chemistry experiments, because we're not really, I mean, look, the number of molecules is usually incredibly large. So back up here, look back up here at this formula, the ideal gas law. We're multiplying capital N, that's a really, really big number, times K, the Boltzmann constant. Look, that's a really tiny number, times 10 to the minus 23rd. There's actually a combination of those things that makes it a little bit easier to work with. And so here's sort of a trick. Here's what we do. Let's convert that N into number of moles. That's usually a little bit more convenient because it's a smaller number. So to do that, Avogadro's number is usually abbreviated as Na, right? So if I divide the number of molecules by the number of molecules per mole, that gets me the number of moles. This thing is what we call the little letter n, little n. Well, if I divide by Na, then I'm going to have to multiply by Na to get that quantity Nk to come out right, capital Nk to come out right. So this thing, if I multiply 6 times 10 to the 23rd times the Boltzmann constant, what I get is a new thing called the gas constant R, which is like 8.31, something like that. Anyway, it's a number like 8. It's a lot easier to plug into your calculator than 1.38 times 10 to the minus 23rd. That's the point. So you can always substitute, if you have Nk, you can always substitute in formulas little n times R. So the way that the chemists write this often is the ideal gas law is PV is little nRT. Right? This is a form of the ideal gas law that's typically for experiments a little bit easier to work with. N is the little n is the number of moles, T is in kelvins, R is that gas constant, 8.31, something like that. Okay, so that was a pretty simple example, but it just shows how to plug the numbers in, how to get the right units. So we'll tackle slightly harder things here to come.